Okay, and we should be live. Let me just check the audio's all good. Just waiting for the stream to load. Okay, 1 2 1 2. Okay, good. I think we're all good on that point. Just so then if yeah, I think we're all good. 1 2. Yeah, okay, cool. Let's get into it then. So where were we? We left off at 1.6. So yesterday we did yesterday we did what did we do yesterday? Yesterday we did oh what did we do yesterday? Yesterday we did oh why am I getting feedback? The controls are a bit. Am I still getting feedback? No, it looks like it's fine. Okay. Um all right, let's continue. Okay, so yesterday we finished off debugging. Good. Yeah, yesterday we finished off debugging, and then we started with types. Data types. So, for example, uh, we did void, void functions, and void parameters. We did object size and the size of operator. We did signed integers, and we learned about bits and ranges. And then we did bits, bytes, and then the ranges of those. Then we did unsigned integers, and then why to avoid them, because unsigned integers can only go from 0 to positive, whereas signed integers can be positive. Or sorry, signed integers can go from 0, from minus to positive. 2 to the power of n minus 1, I think it was. Yeah, 2 to the power of n minus 1. And then we finished off by beginning with fixed width integers. Okay, let's continue. In the previous lesson, we covered that C++ only guarantees that large variables will have a minimum size, but they could be larger, depending on the target system. Depending on the target system. For example, an int has a minimum size of 16 bits, and a a bit is the 2 to the n minus 1, but then your byte, a byte is made up of 8 bits. But typically it's 32 bits on modern architectures. Yeah, we made a note of that here. The various sizes. So you got a short int being 16 bytes, an integer being 16 bytes, a long integer being 32 bytes, and a long integer being 64 bytes. And as he just mentioned there, on modern computers, it is 32 bits for a integer. Okay. If you assume that an integer is 32 because it's most likely, because that's most likely, then your program will probably misbehave. Because remember, we have the ranges of here, which is, as I mentioned, the 2 to the power of n. 2 to the power of n. That formula, where is it? There we go. 2 to the power of n minus 1, minus figure, and then 2 to the power of n minus 1 minus 1. If you assume that an integer is 32 bits, because that is most likely, your program will misbehave. Since you will probably be storing values that require 32 bits of storage on variables with only 16 bits of storage, i.e. that means that you will have an overflow. And an overflow basically means that when it goes over from where was, let me not have it on the main screen. Let me put that here, and then I'll find where there it is. There's the one I was looking for. So that was what I was looking for. So you got an 8-bit with a range of minus 128 to 127, and then minus 32,000, and there's the minus 1, 32,767 rather than 8, and then 7 rather than 8, and then 7 rather than 8. So if you have a 16-bit integer and you go over this, it then spills over, which is called the overflow. Okay. That's what we did last lesson, or last stream rather. Now let's continue. So let's copy this, or not copy this, go into here. We'll get the selector of include, and then we'll do IO stream, and then we'll do a return type of main, and we shall then do an integer and initialize it with 32767, which is, as we talked about there, the range for the 16-bit. Close this. And then if we add 1, x equals x plus 1, and then we do standard character output of x, and then a new line break. Cool. and then we return 0. So then if we were to run that, we would get 3278. That's because I thought it was going to overflow personally, but the reason why it doesn't overflow is because of what we just mentioned, i.e. that typically an integer was 16 bits, meaning it could only be within this range. But in modern computers, modern architecture, an integer is 32 bits, which means that the +1 is not overflowing because we're in 32 bits, and 32,768 is within the range between -2 billion and plus 2 billion. Hope that makes sense. It makes sense to me. However, on a machine where integer is 16 bits, the value does not fit, and as such we will get minus 3732678 because we're going over and we're overflowed. Instead, if you assume int is only 16 bits, your program will behave on all architecture. So does that mean then on all architecture, if we go over 16 bits, we should do long int? Like for example, if we did here short int, I assume we would get minus, we would get overflow. But if we did long int, i.e. 32 bits, we get the same, but it depends on the architecture that you're using, whether it will overflow or not. Hopefully that makes sense. And on systems where int is actually 32 bits, you are not making use of half the memory per allocated per int. In most cases, we only instantiate a small number of int variable at a time, and they are typically destroyed at the end of the function, i.e. the body type. In such cases, wasting 2 bytes, which would be 16 bits per variable, isn't a concern. The limited range is a bigger issue. However, in cases where our program allocates millions of int variables, wasting 2 bits, that is true. Why isn't the size of an integer type fixed? The short answer is that it goes back to the days of C. When computers were slow, C intentionally opted for the intentional size so that it could compile to perform best to the computer's architecture. In that way, we could just use int without having to worry. By modern standards, the lack of consistent ranges for various integral types aren't very good, especially in a language designed to be portable. Okay. Right. Fixed width integers. To address the above issue, C++11 provides an alternative set of integer types. These are called fixed width. These are called fixed width integers. Fixed width integers are defined in the or rather CSTD int as follows: std int 8 1 byte with a range of 8 bits, treated like a signed char on many systems, see note below. std standard unsigned int underscore t 1 byte, and because it's unsigned, it only has the range of 0 to the positive number. Treated like an unsigned char on many systems. And then we have the rest for 2, 4, and 8 bytes. Again, with unsigned only being from 0 to the respective range, which is this formula here. Here's an example. So for fixed width integers, we use the library, or the header rather, the header of, so for fixed width integers, wrong one. For fixed width integers, we use include CSTD int for fixed width integers. Okay, I assume what he means by that is because integer has changed, so because an integer, i.e. int, has changed from 16 to 32 on modern architectures, I assume he means use standard character C, the language C, standard character or standard integer. So that way, when you run something like this, and you do a 32 int, you will always have a 32 integer. And it will always fit, and therefore you won't have to worry about your architecture overflowing. That's what I assume he means. So what I'm going to do is I'm going to take a screenshot of that. And then that's saved there. So here's an example. Actually, what I want to do before the example is I want to do fixed width integers. Fixed width integers. So then I want to copy that modern architecture one. Therefore, we can use fixed width integers to make sure our number we enter is within the range and no overflow or lost data occurs. But the thing is, if you do this, Surely you can just get rid of this and do long int. Or if you really want long numbers, just do long long. Isn't that the same? Why do you need to do standard input 64 bits? Okay, yeah, there we go. Sorry, that was just a fly. Um, I understand what he means by use a fixed width integer type when you need an integral type that has a guaranteed range. But surely it's just a waste, not a waste of, maybe a waste of time to, you gotta include this, then you gotta do this. I mean, the rest is the same, but surely if you just did long, long integer, you'd have no issue. But anyway, that will be personal preference, and as I get more into the projects, I will decide what I want to use, but at least I know it's an option. So the best practice is to use, when you need an integral type that is a guaranteed range. So only when you need it. So there is optionality. Warning, standard input underscore t and unsigned input typically behave like chars. Due to an oversight in specifications, this and this are treated as signed char and unassigned char. The most common is the 8-bit. Okay, let's give that a go just to try it out. So again, the best practice is to just keep going and going and rehearsing and practicing again. So you got include IO stream, and then we want to also above that include language C, what was it, std standard int, and then we will have a return type of integer, and we'll have the main, and then we will have std int ht, and we will initialize that as 65, and then we'll have a std character output of x, and then we'll have a line break, and then we will return 0. So he said that it won't produce 65 because we treat it as a char, i.e. a character rather than an integer. Let's have a look what it does. It produces a, which is a character. Does it produce a every time? It does. A, okay. Let's definitely make a note of that. If using in the header of C standard int and also using what was it, standard, I'm trying not to look so I can remember, standard int 8 underscore t and standard unsigned int 8 underscore t. Was there actually a un, or is it just u? It was just u. Okay. Underscore 8 will behave like chars, meaning if we put a integer into these, it will actually produce a character. And then we'll just copy and paste that because we've already typed the code. Okay, so be careful. So be careful when using those uh, two standards. Two standards. Standards. We'll discuss that in a later lesson. And then we'll just copy that. We'll do warning. I know it's exactly the same, but it's always nice to have it twice, just in case I ever forget. For advanced readers, I'm not there yet, but if you are advanced and you'd like to learn a bit more, feel free to read this on lesson 4.6. Other fixed width downsides. Other fixed width downsides. Finally get it out. The fixed width integers have some potential downsides. First, the fixed width integers are not guaranteed to be defined on all architectures. They only exist on a system where fundamental integral types that match their widths and follow a certain binary representation. Your program will fail to compute on architecture that doesn't support it. However, given modern architectures have standards around 8, 64, 32, and 8, 16, 32, and 64 bits, this is unlikely. Second, if you use fixed, it may be slower. Yeah, this is what I was telling you. It may be slower in terms of, it's definitely slow in terms of typing, but it seems it's also slower on some type of architectures. For example, if you need an integer that is guaranteed to be 32, you might use this, but your PC may be better at processing 64. However, just because your CPU can process doesn't mean that the program will be faster overall. These are just minor quibbles. Fast and least integral types. To help address the downsides, there are two alternative set integers that are guaranteed to exist. The fast types, which are these, provide a fast. Okay, that's interesting. Are we still good? My stream's a bit. We still live? A bit of an error. I just want to pause here, just in case there's something wrong. We still good? We're still good on the recording. Am I coming through on? Yeah, I can hear myself, but YouTube seems to have a bit of an issue. Let me just. Am I still live? Can I still hear myself? Yeah, I can hear myself on the replay. So I'll turn that down so I don't get feedback. And hopefully the lagging has stopped. Has the lagging stopped, or what is the issue? Because I'm getting the stream health. So are we back on, or are we still lagging? I think we're back on. Okay, cool. Let's continue. Right. Fast type integers. Fast and least integral types. To help address the downsides, there are C++ also defines two alternative set integers that are guaranteed to exist. That are guaranteed to exist. Am I still alive? Yeah. That are guaranteed to exist. So what we'll do is we'll copy and paste this. We'll do fast and least integral types, and then we'll do that, and then we'll copy and paste that, and we'll make notes on this. So anyway, to help address the downsides of C++, to help address these downsides of fixed width integers, C++ defines two alternative types of integers that are guaranteed to exist. The fast types, I think maybe the fact that these ads are loading on the page is why the stream might be a bit laggy. But it seems to be all good now. So, fast types, standard input underscore fast hashtag T, and the same but for unassigned. Provide the fastest signed unsigned integer types with width of at least the hashtag bits, where hashtag equals 8, 16, 32, or 64. For example, this 32 one will give you the fastest signed integer type that's at least 32 bits. By fastest, we mean integral types that can only process most quickly by the CPU. The least types, which is basically replacing fast with least, both for signed and unassigned, provide the smallest signed and unassigned integer types with a width of, again, the respective 8, 16, and 32. For example, we'll give you the smallest unsigned integer type that is at least 32 bits. So again, we're using the header of C standard int, but instead of using int underscore t, we will use int underscore least, then the bit size, and then underscore t suffix. So let's give that a go, just to practice. I'll copy and paste that for the notes into here, and then we will try it out. So let's start from the beginning again. We'll include the C standard int, and then we'll also include what we'll include input output stream, and then we'll have the return type of integer for our main function, and then we'll basically copy this for practice because this is the first time I'm doing this. So standard character output as always, and then we do least 8, and then we'll do exertion operator, then we do a size of to find the size of, then we do standard int, and then we'll do underscore least first of all, least 8 times 8. I wonder why. Surely the size of least 8 will show the size, right? Or is it actually bytes? No, it's bits. But we're converting the bits into bytes, are we? Because a byte is made up of 8 bits, isn't it? Why did I write that? Yeah, there we go. A byte is made up of 8 bits. Okay, so we'll then do a quotation mark with bits, and then we'll do a new line. And then what we'll do is we'll just copy and paste that. So that'll be our 16, that'll be our 32, and that'll be our 34. So we'll do 16, then we'll go to least 8 and we'll do 16. and then we'll do 32, and then we'll go to least 8 and do 32 there, and then we'll change that to 64, and we'll change that to 64. And then we'll do a line break underneath that just to get some clarity between it. And we'll do that, and then we'll do it for the fast integers. So standard character output, and then we'll do fast 8, and then to practice that we'll do size of, and then we'll do standard int underscore fast 8, and we'll, like above, we'll times by 8, and then we will do bits with a line break, and then we'll copy and paste that, and we'll do 16, 60, 32, 64. So 16, 16, 32, and finally 64. And then if we run that, we will get least 8 is 8 bits, least 16 is 16 bits, and then so on, and then fast 8 is 8, fast 16 is 16, 32 and 64, and so on. Okay. That's all good. So what we'll do then is we will go to, you can see that least 8 is 16, whereas fast 8 is 32. What? Whereas fast 16 is 32, but it's not. Have I typed it in wrong? Is that why? Have I typed it in wrong? Fast 8, int fast, but it's not. Size of, and then we got fast 8 underscore t. Am I bugging here or what? Standard character output fast 8, size of, standard input 8, fast 8 t. But it doesn't. So why is that the case? It says that our 16 should be 32. But it isn't. And why is that? Is my header correct? Yeah, my header was correct, it hasn't changed. What if we just copy and paste that and see the difference? I'll comment out that, and then I'll do that, and then I'll run it. Why would that be the case? Yeah, is it because I'm using VS Code? Possibly. A 32-bit console. VS Code is a 32-bit console. Hmm. You can see here, well, here it is. So that means, okay. This is because the author's machine, this is because on the author's machine, 32 bits are faster than to produce 16. As an example, let's assume uh, that uh, that the architecture only has 16 and 64 bits. 32 would not exist. So that's why, because, okay. So there's nothing wrong with my code. Um, uh, it was just that potentially um, my architecture is my 16-bit architect on my architecture. 16 bits is faster than 32 bits in this instance. Okay, have these downside. First, not many programs actually use them. I can see why, because you gotta include the header, then you've got to do all of this just to find the size of, and they lead to lack of familiarity. These fast types can waste memory, and the actual size may significantly may be significantly larger. Most seriously, because of their size, fast and least are integers is implementation defined. Your program may exhibit behaviors on different architectures. Yes, as we've seen here, we got 32 in this guy's architecture, whereas in mine we got 16, which could be different to also on yours. So the best practice uh, the best practice for uh, integral types is to avoid them because, yes, because they exhibit different behaviors. Okay, best practice for integral types. Given the various pros and cons, there is little consensus on integral type best practice. Our stance is that it's better to be correct than fast. Therefore, if you need an integral type with guaranteed range, we recommend avoiding fast and least. If you discover later, then you can obviously change it, which is why I said a few minutes ago I would just prefer to use short int, or is it long int, and long int. I believe that's the syntax. Or is it just long and you don't need integer? Yeah, you don't actually need integer. Yeah, long. So you can just do get rid of that. But you do need it on short int, don't you? No, you don't. So you can do short and long like that. Best practice. Prefer int when the size doesn't matter. Ad esempio, if you're asking the user's age, it wouldn't make sense. Yeah, that makes sense because unless someone is older than, or is it 127? No, sorry, 32,000. Then you should be Gucci. I don't want that. Go away. Okay. Prefer this when storing a quantity in a guaranteed range, and prefer this when doing bit manipulation. Avoid the following: short and long integers. Prefer fixed width. Fast and width integers. Fast and least types. Unassigned types 8-bit and any compiler specific width integers. Okay, that makes sense. So when it comes to integral types, the best practice is the following. And then it was prefer std int, and then the other prefer, and then it was avoid, and then okay. What is standard size suffix t? Consider the following code. So let's again practice. Always good to practice. So we'll include the input-output stream. Then we'll have a return type of integer for main. Then within the body we'll have standard character output, size of int, and then we'll have a line break. And we will return 0. What does it print on mine before it prints on his? Let's check. So on mine it prints 4, and on his it prints 4 because we're finding the size of the integer. We can infer the operator size of returns an integer value, but what integral type does the value actually return? An int, a short, a long, a long? The answer is the size of value returns underscore t. Okay, let me just clear my terminal. So then let me set up a new subsection, and we will do what is a standard size t, suffix t. So I'll do that. I'll do that. When printing size of int, the size of operator, or method rather, returns a value of standard size suffix t. This is an alias for an implementation defined unassigned, so it doesn't have the full range of signed, integral type, meaning it only goes from 0 to whatever, meaning the range is only 0 to and then whatever the bit is. Hopefully that makes sense. In other words, the compiler decides if is unassigned, unassigned long, unassigned long. Okay. Yeah, that makes sense. Come on. Go on. There we go. In other words, key insight. It's an alias like we just learned. So size suffix t is defined in a number of different headers. If you need to use it, is the best header. So if you need to use standard size t, we can utilize, spelled in English, the header of, so we would include, and then we would do C standard, and then I assume def means definition. For example, that if you use standard size suffix t explicitly in your code, include one of the headers that defines that. Using size of does not require a header, even though it returns. Yeah, I personally would prefer to keep my code nice and simple, so I would rather use size of, in my opinion. But if you prefer to use C std def, feel free to do so. It's mainly about preference. The best practice is if you, and then I can just copy and paste that. Okay. However, and then using, yeah, cool. Tutto bene. Okay. Much like an integer can vary in size, doesn't mean much like an integer can vary in size depending on the system. Size underscore t can also, and it's also guaranteed to be unassigned at least 16. Okay, that makes sense to me. The size of operator returns the value type yes. So we can use size of operator, and it will actually ask, yeah. Size of operator imposes an upper limit on the object. The size of operator must return the byte size of an object as a value of that. Therefore, the byte size of an object can be no larger than the STD, the standard size it holds. Okay. For example, let's assume this has a 4 bytes in our system, and 4 bytes is 32 bits. An unassigned 4 byte can only go from 0, as we learned in the last stream. Therefore, a 4 byte can hold an object between this. An object with this could have its size returned, so that's fine. However, a byte size, if it was too much, we would not get the object accurately, because remember last time last stream, we looked at unassigned and going over or overflowing. We actually get the modulus, i.e. the remainder, and by modulus I mean the module, which is that, i.e. the remainder, and we lose a lot of data. So if we went to 4,294,967,296, we would get the remainder of 1. No, is it 0 first or 1? But anyway, we would lose this, and we would get either 0 or 1. imposes strict mathematical upper limit. In best practice, the largest creatable object must be smaller than the amount. Some compilers create an object of half the maximum value. Other factors may play different roles as to how much memory your computer has for allocation. When 8 and 16 bits were the norm, this limit imposed rarely had an issue. But as computers get more and more powerful, I assume you have more of an issue. Okay, so that was fixed width integers and size of _t, or suffix t. Introduction to scientific notation. Close this. Come on. Are we lagging again? Just want to check the stream. We still good? Can I hear myself? Yes, I can. Can I hear myself on the video? Yeah, I can hear myself. Good. Okay. Let's continue. Turn that down so I don't get feedback. Introduction to scientific notation. What I'm going to do now actually is I'm going to take a little break. So I'll be back in a minute. Okay? See you in a minute. We good? Can I hear myself? Hello? Oh, yeah. What about on the stream? Yes. Okay, good. Right, let's continue. Okay, so scientific notations. Before we talk about the next subject, we're going to have a sidebar to 9 scientific notations. Shorthand of, oh, hang on, I'm getting feedback. Just turn that down. Make sure my stream is turned down. It is. Okay. Right. Let's cominciamo. Ok, good. And although may seem foreign at first, it's basically the 2 to the power of n, that sort of thing that we were talking about when we were dealing with ranges of signages and unsignages, i.e. this formula here for unassigned and this formula here for signed. Significand exponent, yeah. In scientific notation, it'll be written as this, which is easy to read. Magnitude. Because it can be hard to display or type exponents in C, we use there E or sometimes E to represent times to the power 10 to the power of, yes, which is why sometimes on the calculator you get that. So scientific notation. When use E or E when representing 10 to the power of n. Yeah, Linux users, if you're a Linux user, you might want to read this. Okay, significant digits. Let's say you know the value of the mathematical constant pi, but you've forgotten it. You ask 2 people, one tells you it's that, the other tells you it's that. Both are correct, but the latter the latter is far more precise, i.e. more decimal points. Here's the most significant thing. The digits is a significand. The part before the E are called the significant digits. These significant digits are more precise. So for example, if we were writing pi, we would represent 3.14 as 3.14 E0 because the exponent is to 0. These are, since there are 3 digits, the number has 3 digits. Yes. How to convert decimal numbers. Your exponent starts at 0. If the number has no decimal points on the right side, since the decimal point each place you slide, the decimal point decreases by 1. Trimming off leading zeros. On the left, the significand. Trim off any trailing zeros on the right, the end of the significand. Only the original number had no decimal point. We are not assuming. We are assuming they are not significant. If you have additional information to suggest they are significant, you can keep them. Yeah. Here are some examples. You start with 600.41. You slide the decimal 2 places to the left, 1, 2. So 600 would 600.140 would become 600.00140 e to the power of 2 because we've moved 2 places. No leading trim zeros. Don't trim the trailing zeros. Yes. Starting with this, we move 3 spaces to the right, so that means we deduct after the e. So, for example, 0.0078900 would become, and then if we wanted 7, we would do 1 space, 2 space, 3 spaces. So since we move the decimal point, that would be 1 space, that would be 2, and it actually ends up here, so this is 3, would become 7.890 e to the minus 3. 400 with no decimal points, sorry, not 400, 42,030 would become, so you would move it 4 spaces, so it would be 1, 2, 3, 4, so it ended up here, would become 4.2030 e to the power 0. Yeah, that makes sense. Yeah. Handling trick, hopefully that makes sense to you. If it doesn't, feel free to go over these examples in your own time. Remember, we're on lesson 4.7 at the moment. Okay. Handling trailing zeros. Consider the case where you ask 2 lab assistants the weight. One says 87, the other says 87.00. Let's assume the weighing is correct. In the former case, the actual weight could be that or that. Maybe the scale is more precise to the 1/10 of a gram, or the assistant rounded. When converting to scientific notation, trailing zeros after the decimal are considered significant, so we keep them. So we have 87.0 becomes, we move 1 decimal place, i.e. we move here, we get 8.70 e to the 1. And because we're because despite the fact that this has 3 zeros after the decimal point, we're only moving the decimal point 1. So we do 8, so we move it to the left, and we have 8.7000. But because we've only moved the decimal point 1 space, we still have E1. Yeah. And you could have a million zeros. You would still end up with 8.7, and then you would have a million zeros, and it would still be E1. However, if we happen to know the number being measured precisely, it would be more significant. Yes, it would. So convert, here we go, I'll see if I actually know what I'm talking about. Convert the numbers of scientific notation. Remember, keep the trailing zeros after the decimal point. So I assume that would be, so 34.50 would become, we would move the decimal point 1, so 3.450 e to the 1. Yeah, let's have a look. Yeah, e to the 1, cool. 0 point, how many zeros is that? 1, 2. And then 4, and then 3 more zeros would become, am I still? Yeah, I am. Cool. So we would move the decimal point to the right. So we'll be deducting. So it would be move it once. So move it once here, and we're moving it 3 times actually, not 2 times. So that I assume would be 4 to the power of 4000 e to the minus 3. But you probably could get rid of the 4s, the 3 zeros. Okay, yeah, so we've kept that, minus 3. 123.005. So now we're moving it to the left, so we're adding. So 123.005 would become, so we're moving it to the left, so it's 1, 2, so it would become 1.23005 e to the 2. Yeah, correct? Yes, e to the power of 2. This would become, so 146,000 would become, so we're moving it 1 space, 2 space, 3 spaces, 4 spaces, 5 spaces to the left, so we're adding, so it would be 1.46000 e to the power of how many? 1, 2, 3, 4, 5, e to the 5, correct? E to the 5, yeah, and we can just get rid of that. Okay, cool. Then, okay, so not many. Then 146, again, 4 zeros, 1, 2, 3, 4, 0.001 would become, this time, because we have decimal points, we will want to include the zeros. So we would be, it is 4 zeros, right? 1, 1, 2, no, it's 3 zeros. 3 zeros. So we're moving it 1 space, 2 space, 3 space, 4 space, 5 space, same as above, but we have a decimal point. So that would become 1.46 1, 2, 3, 1, 2, 0, e to the 5. Cool. Then the next one, we'll be moving it to the right, so it'll be a negative number. So it is 0.1, 2, 3, 4, 5, 6, 7, 8, 9. 9 zeros. 1, 2, 3, 1, 2, 3, 1, 2, 3, 8 would become 8 to the power of e minus 9, right? Because we're moving it once, twice, 3, 4, 5, 6, 7, 8, 9, 10. So it would actually be 10 because we want to move it after. We want to move it after the 8. Is that right? E to the 8 minus 10. Cool. And then finally, the last two, 34,500.0 would become, and we're moving it 1, 2, 3, 4. So it would be 3.4500 e to the 4. I assume we don't need to include this, right? Or do we? With 6 digits. 1, 2, so we do, because there's a decimal. Okay. And assume you have 0 knowledge of that. So we will just get rid of the zeros because there's no decimal point. So then 164,000 would become 146 e to the 1, 2, 3, 4, 5. Is that right? Cool. Oh no. Assume you have knowledge that zeros are significant. Okay. 2, 3. But it's the same anyway, surely. Okay, cool. Floating points next. No, thank you. Floating points, i.e. doubles or decimals. In non-computing, it would basically be called a decimal. So, floating points. Like if you want to find the weight of something. Okay. Digits are great for counting whole numbers, but sometimes we need a fractional component. A floating point type variable is a variable that can hold a number with fractional component. Yes. Floating point refers to the decimal point that can float. That is, it can support a variable number of digits before and after the decimal point. Floating point data types are always signed. Okay, so like signed integers can hold positive and negative numbers. Okay. When writing floating point into your code, the decimal separator must be a decimal point. Okay, so I'm from England, so I would use a decimal point. But if you're from a different country that uses a comma, you'll need to use decimal points for this. C++ floating point types. So C++ has 3 fundamental floating point types. A float, a double, a long double. A float, a double, and then a long double. Of 4 bytes, which is 32 bits. And then a double has 8 bytes, which is 64 bits. And then a long double has either 8, which is 64 bits, 12 bytes, which is 8 times 12 is 96 bits, or 16 bits. And I don't know 8 times 16, so I'm just going to Google it. 8 times 16 is 128. 128 bits. Cool. On modern architectures, floating points are conventionally implemented. A float is almost always 8. A double is 8 bytes. Sorry, a float is 4 bytes. A double is 8. And a long can be in between the range of 8, 12, or 16 bytes. Okay. And it's recommended to avoid a long double. Okay. Floating points, floating point variables, and literals. Here are some definitions. Here are some definitions of floating point variables. Yes, we're defining them here. When using a floating point literal, always include 1 decimal place, even if the decimal is a 0. This helps the compiler to understand the number is a floating point and not an integer. Okay, makes sense. The best practice when using is to always make sure your type of literal match the type of variables they're being assigned to or used to initialize. Otherwise, it will lose its precision, most likely due to overflow. So we can get rid of always. Cool. Printing floating point numbers. Now consider this simple program. So we got a return type of integer, we got the library of iostream, we have a main function, we have the character output of 5.0, we have 6.7 floating point, and then we have a long double. The floating point literal, I definitely need to make a note of that. Okay. So, how are we looking? Good. The result of seemingly simple program may surprise you. So we got 5, so it's actually gone down and it's narrowed to 5. 6.7f has gone down, has kept at 6.7, and here we have the significand, we have the E. In the first case, printed 5, even though we passed in 5.0. I believe that's because by default it's a narrowing, so it cuts off. So if we had put a double 5, maybe that would have helped. In the second case, the number prints as we expected. In the third case, a number prints a scientific notation. And then the range, I will, yeah, there we go. I will screenshot this for future reference. So again, we have a positive, negative range. Floating point precision. Consider the fraction a third is actually zero point with a bunch of 3's to infinity. If you were writing this on a piece of paper, you get tired. But on a computer, we have infinite precision. The precision of a floating point defines how many significant digits it can replace without information lost. So, probably make a note of that. Floating point precision. The number of digits of precision of a floating point depends on the, both on the size and their particular value being stored. For example, a float with 6 to 9 digits of precision. This means it can exactly represent any number up to 6 significant digits. A number with 7 or 9 significant digits may or may not be represented exactly depending on the specific value. Which I think refers back to this, doesn't it? Yes, the precision. Okay. Come back to that later. Double values between 15 and 18 digits of precision, with most double values having at least 16 digits, significant digits. That's a precision of 15, 18, or 33. Because we have 8 bytes, 12 bytes, and 16 bytes. Which is why long double has different levels of significant digits. A floating point can only represent a certain number of digits without information loss. Yes. Outputting floating type values. When outputting them, standard character output has a default precision of 6. That is, it assumes floating point variables are only six significant digits, i.e. a float, and hence will truncate anything after that. So 6 significant digits. So we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 5, 6, yeah. So that's actually an important thing to note. So if using standard character output and a float, the standard character output only has storage for 6 significant values and will cut off anything after that. So yes, we can see the program here outputs those values. Get out of here. There we go. Sorry, that's just a fly. Note that each of these significant digits, each of these only has 6 significant digits. And we're using the scientific notation here for these ones, for this one. As such, we'll switch, depending on the compiler, the exponent type to be padded with digits. Fear not that with 2 extra zeros on the 6 is the same as that, with just 0 padding. That makes sense. We can override this precision. We can then override this with an output manipulator with the function named standard set precision, which I haven't looked, but I'm pretty sure that's what we talked about last time when we were talking about size of, and we were doing set width, weren't we? Yeah, IO manip, right? I'm pretty sure that should be IO manip in C++. Is that what we were doing? Yeah, because I'm pretty sure I typed in what is, there we go. Last stream I did that. Yeah. We use the IO input output manip for manipulation library for this. So the syntax would be, we would include the library of input output manip, and then we would use set precision. Then we would use set STD, standard set precision. Cool. So let's give that a go. So we'll include the library. We'll include the library of input output manip, and then we'll include the library of input output stream, and then we'll do an integer of, we'll do a return type of we will do a return type of integer, and then we'll do standard character output. Now remember that standard character output, the default is 6 significant values. So we need to use set manipulation for that. So std set precision 17, and that will show 17 digits of precision. Whereas the standard character output only has 6. And then we'll just copy and paste that because I don't want to type out all of that. And then we'll run it. And then we'll have how many digits is this? I would have thought it would calculate that. How many digits? No. No. Forget it. Because we set precision to 17, the above is printed with 17 digits. I'm just going to get nice up and close and personal. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yeah, 17. Okay, so we know that works. And let me put that as an example here. So an example of this would be and then we do indent it a little bit. Okay, cool. And then we can do the same for the scientific notations. Cool, that makes sense. So the best practice is to favor double over float, because float has 4 bytes, double has 8, I believe, if my memory is correct. Yes, float has 4, double has 8. So float has 32 bits, double has 64 bits. Okay, where were we? Rounding errors to make floating points comparisons tricky. Floating point numbers are tricky to work with due to the difference in binary. Binary, how the data is stored, and decimals, how we think or usually think in numbers. Consider a tenth or 0.1. However, in binary, it would be this. So we can use set precision for that. So we have a double with the assignment of D, and we are outputting D, and because it's only a standard precision of 6, whereas if we use set precision of 17, we would get the actual binary number. And then we get into all this kind of stuff because we get this is not equal to 1 because of rounding errors, but it's 0.99. Okay. Nan and inf. If you've I found that when dealing with JavaScript, I've experienced a lot of nans, not a number, especially if I'm dealing with when I'm trying to sort an array or something, because for some reason in JavaScript, the numbers actually become a string, I believe, if you sort. I think that's the case. In JavaScript, when using sort in an array, do numbers become strings? I think they do. Yeah, they put elements into strings. So when you try to then make so that results, I think you then have to pass and then JSON.pass and JSON.stringify and all that kind of stuff. So that's where I've dealt with not a number on multiple occasions. And if you're beginning and you see that, it can be quite frustrating. But let's deal with it in C++. So, right, floating points, copy and paste that. And now we'll do nan and inf. If I can actually copy and paste correctly. There we go. Nan means not a number. Number capital. No, I don't want that. Inf is infinity. Cool. And it can be positive or negative. Positive or negative. And then we have a signed 0. Signed 0 can be +0 or -0. So we got a double of 0, we got a double of 0 being initialized with 0.0. We have a double positive infinity, which is a double of 5.0 divided by 0, and that will print. So we'll get positive infinity, and then we'll have a double negative infinity where we're dividing by minus the double of 5.0. Then we'll have a 0 divided by positive infinity, and then we'll do -0 divided by negative by positive infinity, and then we'll have the double of not a number being 0, this divided by 0, and the result is infinity, the result is -infinity, the result is 0, -0, and not a number, because you cannot divide 0 by 0. Yeah. Avoid 0.0 when it even if your compiler supports it. So the best practice is to avoid using 0.0 even if the compiler supports it. Okay. So to summarize, 2 things you should remember about floating point numbers. Floating point numbers are useful for storing large or very small numbers, and floating point numbers have the same rounding errors even when the number has fewer significant digits then their precision. So we can use the library of IO manip and then use set precision. Okay, cool. I will copy that here. And then we'll do that, and we'll do that. My bad. That should be 2, and that should be 1. Cool. Okay, so booleans next. Or boolean, or however you want to say it. Booleans. Boolean, i.e. true or false. And this is something you'll come across quite a lot in either C++, I assume, or definitely other languages. So a Boolean is something that is true or false. Yeah. What is the time? So the time's around 12 o'clock. So I'm going to take a quick break before we do Booleans. Where are we? We're at Booleans. Okay, so Booleans, then we're doing if statements, then we're doing chars. So we'll probably finish fundamental data types today, and then tomorrow we can move on to constants and strings. Okay, I'll take a little break here, and I'll be back in a minute. Okay, and we're back. Right. We still good on the volume? Let's have a look. 1, 2, 1, 2. And how are we looking on the stream? Okay, good. We're still good. Still got volume, still got everything. Okay. Let's now move on to Booleans. Why not? Okay, Booleans. Yeah, so a Boolean is either something that is either true or false. So, named after someone called George Boole. So only two possible values, i.e. true or false, to declare a Boolean. To declare a Boolean, we use bool, the keyword of bool. We use the keyword of bool. Bool B. Cool. To initialize it or assign it, we use true or false. So bool B, I'm not going to create examples in main at the moment because this is fairly straightforward for me. But if you would like to do it and get practice in Booleans, feel free to do so. But if he provides more complex examples, then I probably will use it or follow along. Okay. Boolean B1 is initialized as true, sorry. Boolean B2 is initialized as false, and then they've set B1 to false. You cannot, oh no, you can. Default initialized to false. Okay, so if the Boolean does not have initialized value, e.g. bool b3, then it will have a default value of false. Just as the unary minus operator can be used for negative, the logic is the logical not operator, i.e. exclamation mark, can be used to flip a Boolean from true to false or false to true. Yes, we can use the not of operator, aka this, to flip a Boolean. To flip a Boolean. Booleans are not actually stored. Are not actually stored in Boolean values such as true or false. They're stored as integral values. True is 1 and false is 0. Stored as integral values with true being 1 and false being 0. So true equals 1 and false equals 2. That makes sense to me. Similarly, when Boolean values are evaluated, they don't actually evaluate true or false. They evaluate 0 being false and 1 being true. I assume that's because computers speak in ones and zeros. When we print Boolean values, std prints 0 for false and 1 for true. So we have the library of IOStream. We have a return type of main for the main function. We have a character output of true, and we have a character output of not true, aka if something's not true, it's false. We've set Boolean b with the initialization of false. We then print b, and then we print not false. So we should get 1, 0. I'm trying not to look just to practice. So b is false, so it'd be 0, and not b is true, so it'd be 1. So 1, 0, 0, 1. Cool. Using standard bool alpha to print true or false. Okay. Sorry, false. If you're following along my notes, that should not be 2, that should be 0. Because false prints 0. Using std bool alpha to print true. So if we want to print true to true or false, instead of 1 and 0 respectively, we can use standard bool and then alpha. So yeah, so that will print 1, that will print 0. Standard bool alpha prints bools as true or false. Oh, so it actually turns it on. It doesn't actually. Okay. However, it is important to know that if you do this, will not actually print anything. It just acts like a switch, i.e. turning 0, 1 and 0 into true and false respectively. We can then use std non-bool alpha to turn that off and go back to what? Go back to 1 and 0 for true and false. Okay. That makes Makes sense. Okay, just checking my feedback. Cool. Okie dokie. Integer to Boolean conversion. When using uniform initialization, you can initialize a variable using integer literals, 0 for false and 1 for true. But you should be using true or false. So that will produce false, that will produce true, and this will not produce anything. So we'll do false or 0 will produce 1 and nothing. However, in context where an integer can be converted to a Boolean, the integer 0 is converted to false, and ensure any other integer is okay. So if using std standard character output, standard bool alpha for a switch, any number above 0, i.e. 1 and onwards, will always be converted to true. That's interesting. So that will produce true then, and that will produce false. Interesting. Note may generate a warning. If so, you have to disable warning errors. Inputting Boolean values. Inputting Boolean values using character input sometimes trips up programmers. So let's try not to trip up. As we know, if we have an uninitialized, the default will be false. So let's hide the comment there just to make sure I don't see it. So we have a library of IOStream. We have a return type of main for the integer. We have a return type of integer for the function main. We set the Boolean and an empty Boolean, an uninitialized Boolean, to be empty, so it's false. We then have a character output of enter a Boolean value. We then allow the user to enter a Boolean, and then you have entered B. So you would have to enter true or false. So let's actually give that a go, because I actually want to see before he tells me what actually happens. So I'll get rid of that. We'll include IOStream, and then we'll have the return type integer of, and then the main, and then we'll have the character output of enter. No, what we'll do first is we'll initialize the Boolean to be false. This uninitialized value will always default to false. Enter a Boolean value, and then we'll allow the user to enter a Boolean value. boolean b, and then we will simply return b. No, we will produce a character output of you entered b, and then a line break, and then we'll return, because our return type is an integer. Let's actually see what happens. Do we have to do we enter? You entered 1 because it's true. But what if we entered true? You entered 0. What if you did false then? That's why, because we haven't turned on bool alpha. std bool alpha. No, sorry. std character output bool. That is how we initialize it, right? No, it's just std bool alpha. std bool alpha. That acts as a switch. So then, what if we did 0 now? You entered 0. What if we did is screaming at me saying, oh, okay, that's why, because we do actually need a character output, and then the character output is the boolean alpha. So we do std character output, and then the character output is bool alpha with a semicolon. So let's clear the terminal, and then let's, it's still complaining at me. You've entered false. Okay. Because it's not character output, it's actually character input that we're looking for. Okay, okay. So we need to get rid of this, not the body. And then we actually need to do std character input insertion std alpha, no, boolean alpha. Okay, now it won't scream at me. And then if we did, for example, 0, you entered 0. If we entered 1, we entered 0, because they're numbers. But if we entered true, you entered 1. So does that mean we can set our boolean to be true? You entered but yeah, that so there must be a way to convert B into an alpha. Because I've done that, that's okay, okay. So if we are asking for a Boolean input, i.e. std character in, and then whatever. We need to also convert the cin into std bool alpha. Then to get the correct response via we need to then switch on the bool alpha for std character output, such as the following example. So then we would switch on std bool alpha for std input, and then we need to switch on std bool alpha for the character output. Okay. So standard character output bool. Oh no, because I'm forgetting the std. std bool alpha. So now, if we did 0, we would get false. Cool. And if we did anything above 1, we would get true. No. But what if we did 1? We would still get false. What if we did the words true and false? True gets true, and false gets false. Okay. Yeah. Enabling std for input will only allow lowercase true or false to be accepted. Variations with capital letters will not be accepted. So how then do we change that? So what if we commented out, clear the terminal first, and then if we commented out that, but then it wouldn't allow us in any way, would it? It wouldn't allow us to input, would it? So let's do false. You entered false. Okay, it would. And then true. You entered false. Okay, might be something to consider in the future. How are we looking on the time? 20 past. Okay, well, okay, Boolean's nearly finished, so we'll finish that. And I didn't actually add the example to my text, did I? Or my notes, rather. So let's add that, and let's copy and paste that. So we'll finish our booleans, and then we will I'll take a little break. Okay, Boolean values are often used to return values to a function that check whether something is true or not. Such functions are typically named starting with is equal or has common denominator. Okay. Yes, that's fairly common in Swift and JavaScript as well. So the Boolean return value is equal with the parameters of integer x and integer y, with the return of x being equal with two equal signs to signify that it's true. So we have here enter an integer x. We allow the user to x is uninitialized. We then allow the user to enter x, enter another integer with y being uninitialized. We allow the user to enter. I'm just hiding what the output is. We then set the character output to be Boolean alpha to print true or zero. So we'll get true or zero. And then the output will be x and y are equal. And then if it is equal, x and y, so surely it should be are x and y equal. So anyway, if you did 5 here and then 6 here, well, 5 and 6 is not equal, so it will return false. 5 and okay, because there's not a line break, and I thought there was a line break for some reason. I misread it. That will actually be on the same line. Okay, that makes sense. But you could just essentially still put this here. Yeah. Yeah, that makes sense to me. Okay. If statements, a very important thing in overall computing. How are we looking in terms of the progress? So we're on if statements. Maybe another half an hour. We might finish today, but I don't really want to rush. So if statements are quite large. Is quite large. So what I'm going to do now is take a break, and we'll see where we are at about 1 o'clock or whenever we finish if statements. Okay, I'll be back in a minute. Okay, and we're back. Again, standard, just check my volume's all good. I can hear myself on my recording and on YouTube. How about that? Okay, good. We're still good. Right. If statements. Okay, if statements. Yeah. If statements. Copy and paste that. Okay. So it's a conditional. So you're checking for what, and then if it is true, then you print this. Else you print this. So the simplest if statement takes the following form. Yes. If statements, if you're new to programming, are very, very important, and you potentially could use quite a lot of them, or I've experienced you can use a lot of them. So the let me just charge my laptop a bit. Where is it there? The simplest rather, simplest, simplest if statement in C++ is if, and then the condition, and then true statement. You can also have else and else if, which I'm sure we will definitely get into. Condition, also a conditional expression, is an expression that evaluates a Boolean value. Yes. I will most likely go quite quickly through this, as I am fairly comfortable with if statements. But again, if you are not, and you are not familiar with if statements, feel free to go through lesson 4.10 more slowly and stop and pause as you go along. If a condition of an if statement is true, then the true statement is executed, i.e. this. If it's false, then this is skipped and we move on to the next line. A sample program using an if statement. So even though I'm familiar with ifs, I will still go through it for those who are not unfamiliar. Apologies for that. That's just wind. So we'll do. Oh, okay, there we go. Good. We'll include the input-output stream. We'll have a return type of integer for our main function. We will have a standard character output of enter an integer. We will then define said integer or make it uninitialized, and then we'll allow the user to enter it. But we forgot to do semicolon, so we'll go back there. So then, if x is equal to 0, i.e. if the user chooses to enter 0, and again we're using double equals to signify is equal to, then we will print or output the value is 0 with a line break. And then we will, so you can see my cursor, my blinking cursor is still in the if statement. So to get out the if statement, you press backspace and then you're out of the if statement. And then you can simply return 0. So if we run the code and then we clear that first, we then run the code, and then if we entered 1, we wouldn't get anything because we haven't set anything for 1 or any other character output. Then if we ran it again and we did 0, we should get this value is 0. So let's press enter. This value is 0. Cool. Let's examine how this works in more detail. The user enters an integer. The condition is evaluated with the equality operator. And the equality operator, this, evaluates if it's true or false. But because the condition has to be true or false, the statement executes. The value is 0 because we entered 0 and this is true. Whereas we entered 1, it was false, so this never ran. If statements only conditionally execute single statement. If we talk about how to do more in a later statement, in a later lesson. If else, yes. So we can have if, and then this runs if it's true, and then we can have an else statement whereby if this is false, then run else. Given the example, what if we wanted to tell the user that the number they entered wasn't 0? So before looking, you could do something as simple as this. You could do else, and then within the else statement, you would do std character output. This value is not 0. And just to make sure I actually know what I'm talking about, hopefully he says, if we entered 1, we should get this. Because this statement is false, so the code goes to the next, and we'll see we have an else statement. Then it will go to standard character output, and then, it will go to the else statement, and we'll see it's true. So hopefully, if I actually did it correctly, we should get the ability to see that other line. So enter 1. This value is not 0. Exactly. Nice. So you could do something like that. Or you could do if not 0. But those are pretty weird, and if you did that, people would look at you weirdly. But instead, we're going to do this. Cool. We can then use something called if else, and the simplest form of that is, I'll just copy and paste that. So there we go. We have an else statement, and then because this is false and not true, the code goes on to the next line, and then we have else. And because this is false and there's no other lines of logic, we print this. Chaining if statements. So we also have else if. We also have else if, which allow us to chain if statements. The simplest form of that is and then what we'll do is we'll do there, and then we'll do else if condition, and then we would do another true statement, something like that. Let's see if he's got one. No, he doesn't have a simplest form. Okay, but that's okay. Chaining statements. Sometimes we want to check if several things are true or false in sequence. We can do that using if-else. So we enter an integer. I won't copy him. Actually, I will to show you. We'll do else if x is less than 0, then we will print out this value is negative with a line break. So then, because we're checking for negative, I guess now it would make sense that if this is not true and this is not true, then that means the value must be positive. So this value is positive. And then we run this. Let's do 0. The value is 0. We'll run it again. Let's do -1. This value is negative. And let's do 1. This value is positive. Cool. And then what you could do is, if you wanted to, you would do that for greater than, and that would become positive, and this would become negative. Yeah, but to follow along, I'll leave it as it was before. Skip that, that's fine. Boolean return values and if statements. So in the last lesson, we obviously learned about the return values in the functions, and with this exact function actually. But we can improve it by including an if statement if we wanted to. So if is equals, and then x is equal to y, i.e. these ones here, we could run this, i.e. they are equal, else they're not equal. And that would produce 5 is equal to 5, and 6 and 4 are not equal. Cool, that makes sense. In this case, our conditional expression is simply a function called is equals. Yes, the conditional is this, i.e. calling this function with this argument, with these two parameters, and then when we call a function, remember, we get parameters. Sorry, when we call a function with parameters, we have to put in the arguments, which are essentially calling the what are they calling? The parameters. Okay. Non-Boolean conditions. In all the examples, our conditions have been true or false. But what happens if it's not a Boolean value? So int x has been initialized as 4 if x nonsensical for the case character output high, else character output by. So we have 4, and we know from the previous lesson, still in the stream, that 0 is false and anything above 0, i.e. 1, 2, 3, and so on, is true. So that would produce true, which means this is true. So that means this one, so it will run high. Yeah, print high. If x means if x is non-zero. That makes sense, yes. If statements and early returns. A return statement that is not the last statement in a function is an early return. Yeah, i.e. this will not run because we've returned. Such statements will cause every function to return the caller to the return statement is executed. An unconditional early return is not useful. Since B will never be executed, we may as well remove it. True. And anyway, it's a void function, so we don't necessarily need return. However, when we combine with if statements, early return provides a way to conditionalize the return of our function. So we have a return type of integer with absolute, and then we have a parameter of integer of x. And if x is greater than 0, return negative x. So early return only when x is greater than 0. And then we return x. So we have a return type of integer, we have a main function, we have a standard character output of abs. I want to remove that. Oh, it says it anyway here. So we have 4. So if 4, so 4 is greater than 0, so that means that this is false. It will print 4. But if it's less than 0, i.e. -3, then we will return -3, i.e. we entered -3 in the argument, but minus is a positive, so that's why it prints 3. Yeah. What is an early return, and what is its behavior? An early return is a return statement that occurs just because before the last line of the function, it causes the function to return the caller immediately. A prime number is a whole number greater than 1 that can only be divided by 1 in itself. Write a program that asks the user to enter a number 1 through 9 inclusive. If the user enters a number within this range, that is prime, 2, 3, 5, or 7, print this digit is prime. Otherwise, print digit is not prime. So let's give that a go. Put me to the test. Include iostream, and then what we'll do is, first of all, we'll create the main, then we'll obviously return 0, and what we'll do is we'll create a function that returns an integer and checks if it's prime. So an integer is prime, int x. Then what we'll do is we will zero through 9. So so I think we need to use a for loop, don't we? So for int equals I, I in the range of 10 and then I plus plus. I don't know if I'm just overcomplicating this. No, that should be, that's why it's not working. And that should be I. Am I just, no, I don't think I need a for loop actually. So if, I think I'm just overcomplicating this. We haven't done for loops yet, so perhaps that is the reason why. So x, uh, if x modulus modulus divided by 1 is equal to 0, then we will, no, hang on, stop. So it is prime, and then no, we actually want int x and a parameter int y as well. And then we want to return a prime whole number. Write a program that asks the user to enter a number 0 through 9 inclusive. Enter a number 0 through 9. So how about we do in here, we'll do the easy part first. Standard character output. Enter a number between 0 and 9. Then we will maybe we don't even need that. I'll leave that for now. We'll do int x unassigned. Then we'll do a standard character input of x. Then we'll do if x divisible by 1 equals 0, then standard character output this digit is a prime number. Else, if it's not, then we will semicolon. Then we will produce the standard character output of this digit is not a prime number. And then what we'll do is we will have a line break and then a line break. Now, am I doing that correctly? Do I even need this? Or is that just overcomplicating it? I mean, what you could do is you could convert all of this into is prime. But we'll copy that out for now. Or another thing we can do is instead of copying it out, we can just do if 0 and then end if. So what if we run this? Will it actually, if x divisible by 1 is equal to 0, Let's see if I've done that correctly. So let's do 2, and 2 is a prime number. This digit is a prime number. Good. Let's do 9. So this should not be a prime number. This digit is a prime number. But 9 is divisible by 3. If x divisible by 1 if x divided by 1 is equal to that, 9, this digit is not. Okay, so we don't need the modulus yet. So where am I going wrong with that modulus then? I might just be overcomplicating, but at least we know now that it's not. So let's just double check that it works, and we'll go 2. But now 2 is printing as not a prime number. If x divisible by 1 is exactly equal to 0, five is a prime number. I think I need to see a hint. We're using else if. That's what I must not have done. Else if x x divided by 1 is greater than 0, then we print this is not a prime number. And then what if we just get rid of that for now? So if x divisible by 1 is greater than 0. No, hang on. Stop. Let's run this. 2 is a prime number. 2 is not a prime number. But that seems so inefficient to do that. Surely there's a better way. I mean, yeah, you can do that, but I understand what he's doing. And also, I just realised that should be Boolean, not integer. Okay, so just to practice, let's go over that. So include IOStream include IOStream, and then we have a Boolean of is prime, and then we have an integer of x, And then we have, I mean, you can do that, I guess. If x is equal to 2, let me just, even though we got it wrong and we needed, or I got it wrong and we need a solution, let's go through it. So std character output, or let's try to do it ourselves. This is not a prime, this is a prime number. Prime number. Else if, or just if? Else if, I hope so. Else if x is equal to, what was it, 3? Standard character output. This is a prime number. And then else if x is equal to 5, we'll do that, and then we'll do else if x is equal to 7, and again we'll just copy and paste that, and then we'll have an else, and then we will return false. Then or then maybe just return false otherwise, so the function doesn't run. Then we will have our main function, and we will have std character output of enter a integer between 1 and 9, and then we will define x being unassigned, std character input, and we will get x, and then we will have if x, sorry, no, if is prime x, if is prime x, then we want to run it, right? If is prime x, so there's that, but then the else statement would be, no, if is prime, return true, and then else return, else standard character output insertions, this is not a prime number, right? I'm not checking the answers, don't worry. This is not a prime number. And then full stop, line break, semicolon. And then we will return 0. Okay. But that just seems so inefficient. There has to be a better way. There has to be. Anyway, let's give it a run. I'm sure as I get better at C++, so return true. This is a prime number, this is not a prime number. Maybe just true. Idiot. Just being stupid. So this actually ends up being returning true, just like all of them. And this is where you enter the standard character output. Okay. He says he knows if statements, but then he does that. True. So then here, why is that causing me issues? If is prime, because we need to do return true, that's why. Return true. Do we need to do bool alpha? Okay, warning. Else if. That's because it's double. Clear. Else return false. I gotta be messing up somewhere here. If is prime. If is prime, and then X as that. Standard character output. This is a prime number. Else standard character output. This is not a prime number. Is it the spacing of here? No, it can't be because it was running anyway. Bool literal is returned. So is that because we need a bool alpha? Bool is prime integer if return true. Yeah. There's something wrong with that code then. I mean, it runs return true. But 9 is not a prime number. 2 is prime. Okay. And yes, I probably should have, I did know about logical operators. That would be a lot easier than writing all this out. I was trying to use modulus, and maybe I shouldn't have because I'm not exactly completely familiar with modulus. So, but there's still an error in that. Oh no, it's not. The error's gone. Maybe it was a typo or something. That's just the change. Okay, so sometimes your IDE can do that. For advanced readers. Question 3 then. Yeah, so we will eventually use switch statements, whereby you would switch X for case 1, case 2, or you could just put them on the same line. Okay. How can the length of the following code be reduced to without changing the format? Okay, so let's practice that. We'll include the IO stream as always. Then we will do a return type of Boolean is allowed to take fun ride, and then we'll create the body, standard character output of how tall are you, and then we'll have a line break. And then we'll have a double where the user can enter their height. We won't use a float because obviously double has more space, if I remember correctly. Height, uninitialized. Then we'll allow the user to enter their height, and then we will have if height, and then the condition we're looking for is so if height in the condition, if height is greater than or equal to 140 centimeters, then we will return true, else return false. Then that closes that, but we need to remember semicolons, that's why that's not working. Then we have our return type of integer for our main, and then we have if is allowed to take fun ride. We don't need to pass in any arguments because the is allowed to take fun ride doesn't take any parameters. Then we have the std character output have fun, and then a line break, and then else the output of sorry, you are too short. So let's take a look at why this won't work. Or this could be better. So, How could the length of the following code be reduced? So this is all about refactoring. I mean, what you could do is you could just get rid of the else, because if the height is uh, if the height is no, that doesn't seem right. You can't. There's no point doing that. There's no point doing that. So if height is greater than 140, return true. But we know that the default is return false. So if we got rid of return false, or we got rid of this, so if we did if and then end if, and we got rid of that, so that doesn't work on if statements. That's interesting to know. So let's just comment that out. Turn 0. Is that the only way you can do it? The only thing you can reduce? You got a double height, std character invert height. Does that still run though, even if we're not returning false? How tall are you? 111. You were too short. Is that the only way we can reduce it? But we get that error there. Where is it there? Line 13. What about now? Non-void function. What about if we did we returned a double? Hang on. What if we added back this? Sorry, you are too short, with a line break. Then what if we actually did double of height? I see there. It's incompatible with Boolean. And then we potentially got rid of that. No. I'm probably just being really stupid. A double of height. If it is allowed. The only thing I could think of is removing this. No, I think I'm going to have to tap out on that one. We don't need to include the if statement. We don't need the if statement in if is allowed. The expression evaluates ball can be returned directly. Okay. return. Okay, yeah. So I was sort of there on my way. So I originally said remove that, but instead of doing that, you can get rid of this and just make it return height greater than or equal to 140 and then semicolon. Still with an error somewhere. 13. What if we ran it again? How tall are you? 10. You're too short. Okay. Yeah, I can see why. So I originally said remove this, but because you remove this, you could also just remove the if uh, and then just have a return because a boolean. Remember, the boolean in C++ always returns false. The default value is false. Keep that in mind. Okay. So what's the time at the moment? 20 past 1. So I think I know we've only got chars, characters, and one other thing left for this, but I think we'll leave that for tomorrow. So we'll leave off at chars, left off at lesson 4.1 chars. Okay. So what we'll do now is we'll clear the terminal first of all. We will do day 7, and then we will do what we learned today. So we did fixed width integers, fixed width integers, I being std int, and then you have all this to print size of. Then we did fast and long integers and why not to use them. Integers. Then we did size of and standard size underscore t. Then we did a bit about scientific notation. Scientific notation. Then we did floating points, i.e. Float, double, and double was it? Long double, and the various bits and bytes. Then we did not a number and infinity. And then we finished off with booleans, and then finally we finished off with if statements, slash else slash if else statements. Okay, so we'll then move on to chars. Tutto bene. And the date today is the 4th of August. Cool. We'll leave it there for today. If you followed along, well done, keep it up. Hopefully you did better than me on that if statement and reducing it. Although I still think that when we were doing the if 1, 2, we could do something better. And as you saw, you can use switch, which I I've used Swift before, and I've used switches before, and I probably should have come up with that, but I didn't. But I'll learn from that definitely, and I'll remember it. Hopefully, remember it for last time. So tomorrow, commit that. Tomorrow we'll be doing, or the next stream we'll be doing chars, i.e., characters, right? Yeah, character. Char is a character. Hopefully you're following along. Hopefully you're enjoying. If you are following along, let me know what you think I should be doing, what errors I made, and just in general what I can improve on. So please like, subscribe, and I'll see you in the next one. All right, bye.